Hello. Today we're going to look at the third way of dealing with volumes of solids of revolution, and that is called volume by the shell method. And the basic idea is, let's suppose that I'll use the same basic area that I've been dealing with, and let's rotate this about the y-axis so I get something that looks like this again. You would think with the amount of times that I've drawn these things I would be better at it, but is not to be. We have the following. This is my axis, etc. Looks something like that. And now, up until this point, we have always made our rectangles that we've rotated to get our volume be perpendicular to the axis of rotation. If, however, we took rectangles that were parallel to the axis of rotation, then in that case, we can also get the volume by moving these, out through. And so what happens is we end up with the situation of what's called a cylindrical shell. Each of these gives us the shell of a cylinder. Basically, just the outside. If you were to take a can and get rid of the top and the bottom of the can, so those are open, just the outside part of that cylinder. And we then stack these one next to the other with varying heights, and when we do that, we then get, and again this is near impossible to draw, we get the particular volume. We can build the volume. It's kind of like dipping a candle, making a candle in wax. They dip it in wax and it puts on a layer, a shell of wax, and you build out. And in that case, of course, the height is fixed, but in this case, what we're doing, the height changes as we move out. And so we can build the volume out that way. And for shells, the shell method, again, how it differs, the rectangle that we rotate is parallel to the axis of rotation. Whereas in the disc and washer method, in both of those, the rectangles are perpendicular to the axis of rotation. Okay? Now, in terms of the overall basic formula that we have, if I take a rectangular, if I take a shell here, and I were to cut down the side and unroll it, I get a rectangle. And so the height of this rectangle is the height of the shell over here. The length of this rectangle is the circumference of the shell. And so basically the volume then is the integral of 2 pi RH. The area of this rectangle is 2 pi RH. To get the volume, I just take these areas and the limits of integration give me the third dimension, and we get the volume. And so Just like before, we got the volume by taking the cross-sectional area and then integrating to get the third dimension. Here I take the cross-sectional area and integrate it, and that'll give me the volume, the third dimension. Okay? So this is the basic form that we use. The radius is going to be the distance from the axis of rotation, and the height is the height of the shell. We'll see that in the examples that I'm about to do. So let's look at some examples. Suppose I have y equals 1/2 x squared minus 5, y equals 3x minus 9, this region, and I want to rotate about the y-axis. And this time I want to use shells. So y equals 1/2 x squared minus 5. This is a parabola that opens up a little bit wide and is shifted down. So something of the nature of like this. And y equals 3x minus 9 looks like this. And so this region is what I'm going to have. I don't really need a better picture than this at this point, because ultimately I'm going to have to find these points of intersection. So I'm going to need to know what those are. Since I'm rotating this around the y-axis and I want to use shells, my rectangle is parallel to the axis of rotation now. Okay, so the first thing I need to do, we will solve, see where these two curves intersect. And so that gives me x squared minus 10 is equal to 6x minus 18, or x squared minus 6x plus 8 is equal to 0, which is x minus 4 times x minus 2, I guess my picture is off a little bit, is equal to 0. I'll fix it in a minute. And so x then is equal to 2 and 4. Actually, it may not be. No, I think it's right, or close enough. X is equal to 2 to 4. So the important values are that this is my x equal 2. This is x equal 4. Again, the variable that we use is always perpendicular to the rectangle. In this case, the rectangle perpendicular to the x-axis, that's the variable we have to use. When we set this up, my volume by shells, 2 pi integral RH. And now we'll put in the details. As I said, the variable is x. It goes from 2 to 4. The radius is the distance from the axis. That radius is just going to be plain old x. Whatever the x value is, that's my radius. The height is the height of this little rectangle. And for that, I need to do top function minus bottom function. My top function was the line, which was 3x minus 9. Variable is x, so that's good. Bottom function was the parabola, 1/2 x squared minus 5. And this is actually the setup. I will simplify this a little bit. 2 pi, the integral from 2 to 4 of x times negative 1/2 x squared plus 3x. Negative 9 plus 5 is negative 4. And then you could distribute the x, and then we can take the integral, et cetera, et cetera. Okay, my second example we have y equals the cube root of x, y equals 1/4 x, and I only want to look at the first quadrant of this. That actually will intersect both in the first and third, and I want to rotate this about the x-axis, and I want to use shells. So you will be told whether you want to use discs or washers or shells. Well, discs and washers, it will depend on the specific nature of the graph. As I said, if the rectangle that is perpendicular to your axis of rotation, we're using either discs or washers, and if the rectangle always hits the axis, it is discs. If it sometimes doesn't, then we're using washers. Shells, you'll be told to use shells. So, in this case, I have the cube root, which looks something like this. Y equals 1/4 x, looks something like that. This particular region, again, I don't care about the third quadrant, rotated about the x-axis. Since I want to use shells, my rectangle is parallel to the x-axis. I need to know these points of intersection. Obviously this is 0, but we'll solve. The cube root of x is equal to 1/4 x. And so x is equal to 1/64 x cubed, or 64x is equal to x cubed. I will then factor, and this factors nicely again, x minus 8x plus 8. And so I get x is equal to 0, 8, and negative 8. We obviously don't need the negative 8 one. So this would be when x equals 0, and this would be when x equals 8. Now, because I am dealing with rectangles that go horizontal, the variable that I need has to be in terms of y. Because the variable that we use is always perpendicular to the rectangle. So I have to change these. Instead of x being 0, we have y equals 0. And instead of x being 8, we get y equals 2. So now I know where my rectangles are going to go from. Y equals 0 to y equals 2. My volume, shells, basic form, 2 pi integral RH. Specifics, variable is y, goes from 0 to 2. Since my variable is y, the radius is y. The radius is x, sorry. The radius has got to be y, sorry, I'm not paying attention here. The radius that we have is, my shell is going to go this way. The radius is the distance up. And I forgot which way we were rotating this thing. And the height is the length of this rectangle. The length of this rectangle is going to be the distance to the outside function, which is the line. The line was y equals 1/4 x. However, I need this in terms of y, and so therefore x is equal to 4y minus the distance to the cube, Again, we have to switch this. X equals y cubed. And therefore, we have what we need. Multiply that out, integrate, etc.